All right, let's look at number 137, and this is 137b. And we're to do a couple of different things with this power series, this function defined as a power series. We're to find its interval of convergence. Then we're to find a power series for f prime of x. And then we're to find a power series for the integral of f of x. Okay, and we're going to do those last two by term differentiation and integration. Keep in mind that we're making use, you'll see this 2n in parentheses factorial, so that's important. We're to remind ourselves of what the factorial notation means, right? N factorial is n times n minus 1 times n minus 2 all the way down to 3, 2, 1. So like 10 factorial would be 10 times 9 times 8 times 7 all the way down to 1. But notice that this n minus 1 all the way down to 1 is the same as n minus 1 factorial. And hence we can write that n factorial is n times n minus 1 factorial. Now keep in mind here we've got a 2n factorial, so 2n factorial would be 2n times what? 2n minus 1, 2n minus 2, 2n minus 3, all the way down to what? 3, 2, and 1, which is the same as, notice, 2n times 2n minus 1 factorial. Okay, so we'll be doing a lot of manipulations like this in a little bit, so I wanted to make sure that you're familiar and recall those ideas. Okay, it's helpful to, I think, list out the terms in our series, not to find the interval of convergence, but to do the term-by-term differentiation and integration. So when n is 0, I get x to the 0, which is 1. 2 times 0 is 0. Factorial is 1. So keep in mind that 0 factorial is equal to 1, and 1 factorial is equal to 1. But 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6, and so on. Okay, but we'll start there at 0. When I do n is 1, I'll get x squared over 2 factorial. I wrote it this way, but you could just write it as x squared over 2 factorial if you want to, a little more compactly. Okay, and then when n is 2, so n is 0, n is 1, n is 2, I get x to the 2 times 2, x to the 4th over 4 factorial. N is 3, I get x to the 6 over 6 factorial, and you see the pattern, x to 8th over 8 factorial, and so on. Okay, let's first find the interval of convergence, and I'm going to do that by the ratio test. I'm going to find the values of x, right, for which this series converges absolutely. I'm going to take the limit as n goes to infinity of a sub n plus 1 divided by a sub n, and recall that I can think of this as a sub n plus 1 times the reciprocal of a sub n, and that's what I'm going to do here. So a sub n plus 1, now be careful, when I replace n with n plus 1, I get 2 times the quantity n plus 1, written that down here, which if I distribute the 2 is actually 2n plus 2. So when I plug in n plus 1, I get x to the 2n plus 2, right? And if I replace n with n plus 1, I get 2n plus 2 quantity factorial. And notice 2n plus 2 quantity factorial is 2n plus 2 times 2n plus 1, right, which is 1 less than 2n plus 2. And then 1 less than 2n plus 1 would be 2n. And then we would continue 2n minus 1, 2n minus 2, 2n, and so on. But all the rest is 2n factorial. That's real important. That's making use of this idea that I have up here, right? Times the reciprocal of a sub n. So I just do the reciprocal of this thing, 2n quantity factorial over x to the 2n. Notice x to the 2n plus 2 by the rule of exponents is the same as x to the 2n times x squared, right? Because we add the exponents when we're multiplying. But now you see what happens. I can divide numerator and denominator by x to the 2n. I can divide numerator and denominator by 2n factorial. And what's that leave me? Just up top, an x squared. And on the bottom, 2n plus 2 times 2n plus 1. Okay. Now this x squared doesn't change as n goes to infinity. So I can pull it outside. Of course, it's the absolute value of x squared. Of course, the absolute value of x squared is the same thing as x squared because x squared is always positive. Okay. And again, in this ratio test, keep in mind that we're running this test assuming that x is not equal to 0, because we know clearly if x were 0, we would be adding a bunch of zeros up, and that would converge. And so obviously this power series is centered about 0, converges at 0. We're trying to find what other values of x it converges at. Okay, so what's left is the limit as n goes to infinity of this stuff in the bottom, 1 over this stuff. Notice absolute value bars I can get rid of because 2n plus 2, 2n plus 1 are positive as n goes to infinity. So it's just the limit of this thing. But clearly this is going to go to 0 because 2n plus 2 times 2n plus 1 is going to infinity. 1 divided by a larger and larger value is approaching 0, regardless of the value of x. I mean, x can be a billion, and this thing is still going to go to 0. And so a billion times something going to 0 is going to go to 0. And what this means is, by the ratio test, if this limit here is, again, less than 1, if you remember, here's from our summary sheet for the ratio test, if that limit is less than 1, right, then we're talking about convergence, right? And it's going to be absolutely convergent in this case. Right. And so clearly 0 is less than 1, so our series converges absolutely for all x. That means our radius of convergence we write as infinity. The interval of convergence, which is actually what we're asking for, is, just all real numbers, which we write in interval notation that way. Okay, so that's really good. It's convergent for all values of x. Now let's go back and let's find the derivative f prime of x. So first of all, term by term, all we do is we take the derivative of each one. What's the derivative of 1? Derivative of any constant is 0. So I've got 0 down here, right? What's the derivative of 1 over 2 factorial x squared? Now I know 1 over 2 factorial is 1/2, right? 2 factorial obviously is equal to 2, but I'm going to leave the factorial notation in there, and you'll see why. So how do I take the derivative? This is a constant multiple, pull it out. What's the derivative of x squared? Bring the 2 down, subtract 1, I get 2 times x. 2 times x, right? So I'm going to bring the 2 down rather, over the 2 factorial times x. Now I know 2 divided by 2 factorial is just 1, and you can simplify that, but I'm going to leave it like that for just now. Okay, now what's the derivative of the next term? Bring the 4 down, it'll be 4 over 4 factorial x what? Subtract 1 cubed, 4 over 4 factorial, right? X cubed. And then what? Bring the 6 down, 6 over 6 factorial x to the 5th. And then we'll bring the 8 down, 8 over 8 factorial x to the 7th. Now we can simplify these, and we can, this was 1, but what I'm going to do is to note that 2 factorial is 2 times 1 factorial. 4 factorial is 4 times 3 factorial. 6 factorial is 6 times 5 factorial, and so on. So I can actually cancel the 2's here and be left with a 1 factorial on the bottom. Yes, 1 divided by 1, this is just 1. It's just x, but I like to put it in this form. 1 divided by 3 factorial, right? Because the 4's cancel here. X cubed, the 6 cancels here, leaving 1 over 5 factorial, and so on. So you can sort of see it's just x to the first over 1 factorial, x cubed over 3 factorial. I mean, if you want to actually simplify, 1 factorial is 1, so I get x. 3 factorial is 6, I get 1 6x cubed. 5 factorial is going to be what? Oh goodness, 3 factorial 6 times 4 is 24 times 5 is 120, right? And so on. So I mean, if you actually want to put the numbers in, but I like this way. So now this is term by term, but what about the actual summation notation? How does that going to change? So if I go to the summation notation here, what do I do? If I take the derivative of this thing, the 2n factorial is a constant multiple, right? So I can just take the derivative of x to the 2n, bring the 2n down, right? 2n x to the what? Subtract 1, 2n minus 1. And that's what I've done down here. I've brought the 2n down, x to the 2n minus 1 over 2n factorial. And that actually matches up very well with my first line here, my term by term if you plug in n equals 0, right, you get 0. If you plug in n equal 1, you'll get this. If you plug n equal 2, you get this, and so on. But I can simplify because remember, 2n factorial is 2n times 2n minus 1 factorial, right? And so the 2n and that 2n cancels, and I have x to the 2n minus 1 over 2n minus 1 factorial. And that's the answer. Notice that this matches up. If I plug in n equals 0 here, what do I get? 0, I get x to the negative 1. So obviously I actually have to cut off that 0. What happened to that 0? Well, if you remember, that term right there, right, the derivative of the first term was 0. So I actually have to change this technically to start at 1 in order for it to match up with what I have here. Okay, that first term, that term that we initially had at n equals 0 was 1, and the derivative of that was 0, so it's gone. So notice this formula is not going to work if you plug in n equals 0 into it. Okay. This formula here is not going to work if you plug it. It will work up here because we have the 2n, and now that we've lost that, right, we don't want to deal with a negative factorial. But with n equal 1, now we'll start 2 times 1 is 2, minus 1 is 2. I get x squared. Sorry, 2 minus 1 is 1. I'm just having all sorts of trouble. 2 minus 1 is 1. I get x, right, over 1 factorial. Thank you. That's the first term, x over 1 factorial, which is just x. And then when n is 2, I get 4 minus 1 is 3, x cubed over 3 factorial. That's that term, right? When n is 3, I get x to the 5th over 5 factorial. When n is 4, I get x to the 7th over 7 factorial. Okay. Woo. All right. So it's gonna give you those same values as a check, right? You can check that out. Now let's talk about integrating term by term, okay, to get the integral. So when I integrate this function, again, I'm going to look at it term by term first, and then we'll look at the summation notation. So we start with our constant of integration at the beginning because it's an infinite series, right? Dot, dot, dot at the end. We want to make sure that we include that constant of integration at the beginning. So what's the antiderivative of 1? It's x. What's the antiderivative here? Well, I've got, again, I'm going to think about it as x squared over 2 factorial. But the antiderivative of x squared is what? We add 1, right, x cubed, and divide by 3, right, x cubed over 3. So I've got x cubed over 3, and then that 2 factorial is still down here, right? That's the antiderivative of this first term. This one will be what? X to the 5th over 5 times 4 factorial, right, times that 4 factorial. X to the 7th, 7 times 6 factorial. X to the 9th divided by 9 times 8 factorial, right? So there's the integration. Now I can simplify these a little bit, right? Because notice, what is 3 times 2 factorial? That's just 3 factorial. What's 5 times 4 factorial? That's just 5 factorial. What's 7 times 6 factorial? That's 7 factorial, and so on. Okay, so there's a nice way to write out term by term the integral of the function. So what about the actual summation notation? Well, I could do the same thing here, right, to this term, right? So we get the constant plus what? If I antiderivative x to 2n is what? X to the 2n plus 1 divided by 2n plus 1. And this 2n factorial is still down there. That's just a constant multiple. All right, so I can just pull that out. 1 over 2n factorial, not out of the summation, but out of the integration, right? And then x to the 2n plus 1 over 2n plus 1. There's the antiderivative. Okay, and that's the way I can write it. But notice 2n plus 1 times 2n factorial is 2n plus 1 factorial. So this down here is all just 2n plus 1 factorial. And there's our integral of our power series. And you can check again when n is 0. If I plug in 0, let's see if this works this time. 0 plus 1 is 1. I get x over 1 factorial, x over 1, or x. When n is 1, I get x cubed over 3 factorial. When n is 2, I get x to the 5th over 5 factorial, and so on. So I'm getting all those. The nice thing about all three of these power series, the original one and the one that we got for the derivative down here on the left, and the one we got for the integral, their interval of convergence is the same, right? Which is all real numbers. So these power series all have an interval of convergence of all real numbers. Okay, so I hope that kind of explains the process of, term by term differentiation and term by term integration.